Okay, I will give you your first two view quiz answers. And they are the letters A and D. A as in apple is your first one, and D as in dog is your second view quiz answer. A and D. All right. Let me now show you kind of, I guess, a slightly neater application of our neural network. And I'm going to apply this to the MNIST handwritten digits dataset. And you can download these scripts and it will run as well. Let me download the script. Did that work? Actually, so I have it over here. I hope this still works. Okay, I don't know if you are familiar with the MNIST handwritten digits dataset. It is the MNIST database. It looks like this. So, yeah, one of the early kind of implementations of neural networks and this software and stuff was came from like the post office. Okay, so they wanted a way to be able to route like letters that were where the address was handwritten. Okay, and you have like these zip codes, and it used to be manually sorted. Like there would be a person and they would look at a letter and they'd say, oh, okay, the first number is a 9, so it's going to go over here. And the next number is a 7, so it goes over into this thing. And they would look at that. And then, so 9 is everything like on the West Coast. And then you'd have another sorting facility, and it's like, okay, these are everything with a 9. And then we'll look at like, okay, the first 3 digits, and then, 9-1, so that's Southern California or whatever, So you have... you had all of these handwritten digits, and they wanted to kind of speed things up, have the computer do it. And so somebody went through and scanned all of these kind of addresses, and then they isolated the zip code, and then they cut them up into these perfect little squares, okay? And so this was a lot of work of preparing this data set, okay? And there's, I want to say there's like 70,000 images, okay? 60,000 training images and 10,000 testing images where some, people went and they scanned all of these things and they cleaned everything up. So you have these perfect 28 by 28 pixel images, okay? Each one kind of centered on a number, and then they know what the numbers are supposed to be, because it would say like this one is going to Los Angeles, or like Beverly Hills, right? Zip code 90210, right? And so they say, okay, we've scanned these numbers and we know this is 90210 because it's going to Beverly Hills or things like that. So they have all of the numbers and they have them all labeled, and they have 60,000 training images, 10,000 testing images. And the question was, can we get our computer to recognize digits so it can start sorting these things for us, okay? And so this is what the testing data set looks like. This is the colors are inverted, where the background is black and the digit is written in white. Sometimes you see the opposite, where the background is white and the number is numbers in black or something like that. So it's basically the same thing, but just like inverse colors, okay? And when you look at one of these numbers, okay, I think the original data, the values go from 0 to 255, okay? So it's you have 256, I guess, shades of gray, okay, where the max level is going to be black and the minimum level will be white, or however versus, and then somewhere in between. And then what we're going to do is we're going to scale them so that the max value is like 1 will be like white, and then 0 will be like black or something, or flipped and reversed. Okay, there's actually a this video will show it. I don't want to if I play it and record it, I'll get a copyright strike, so give me a second. As far as our network goes, I have just one hidden layer with 30 neurons, okay? But you can download the MNIST data directly. It's on it's available here, okay? And if you do download it, it downloads as these .gz files. These are like I don't know, gzips. And so if you have a Mac, wherever you download it, you're gonna run the command gunzip, okay? Gunzip, and then the file name .gz. You're gonna have to, there's 4 files. There's the training images and the training labels, the test images and the test labels. So you'll have to run this 4 times, gunzip, training images, gunzip, training labels, so on and so forth, okay? If you're on a Windows machine, you'll probably have to download some software. There's an excellent free software called 7-Zip that handles zipping and unzipping of all sorts of file formats. That's the one I recommend. You can download 7-Zip and it will unzip these .gz files. And if you and I recommend creating a folder called MNIST somewhere on your computer, and it will unzip them into these .ubyte files, okay? IDX3 ubyte files, which, I don't know how it works. Okay, but anyway, you get that onto your computer, and then you can load this onto your machine. There's this script called load MNIST, and this will, what do you call it? Import all of this binary data, because the files that are in these ubyte things. You might have to adjust, like if you don't, this is assuming you have a full subfolder called MNIST where these files are. If you change the name of your subfolder, you might have to change the name of the path there. But anyway, I'm going to just run these things, and that will load the data into our thing. So I'm going to, no, something failed. Cannot open the connection. Well, I'm probably in the wrong working directory here. Okay, I think. Let me just clear my environment again. Run that. Okay. So yeah, you might have to just make sure you set your working directory correctly. And so here I have it, and so it's loaded in here, and you can see test is this. There's 10,000 images. Okay, so we have 10,000 labels, and then our X matrix has 10,000 rows, 1 row for each image. And each image is basically 784 values, a vector of 784 values, okay? Same thing with kind of train. And so if we want, and train has 60,000 images. So let's say if we want to just look at the first image in our training data set, I can just say, hey, let's look at row 1, J is going to be 1. I can extract out the label. The label on J, on that first row is 5. And then the digit is just these 784 values ranging from 0 to 255. Okay, so these are all zeros. Some of these are like 253. Okay, and I can show that digit. Okay, and this is what it looks like. So the zeros are basically on this plot, 0 corresponds to white, and 253 or 255 corresponds to black there, okay? So it's just kind of the inverse image of what's in the video. And yeah, our network structure is going to have 10 nodes in the output layer, with one node corresponding to each possible label. Okay, so one node will correspond to label 0 and label 1, and then the last one will be label 9. Now we need 10 nodes, one for each possible label, because this is, at its heart, it's a classification problem. Okay, it is not a regression problem. So regression problems is you're predicting a number, and it feels like, well, aren't we predicting numbers? Okay, but we are labeling an image, which is different. So with a regression problem, your error is how far off you are. Okay, so if the true answer is 9 and you guess 8, that is a better guess than guessing 1, okay? Because we're saying 8 is closer to 9 and 1 is far away from 9, so 8 is a better guess than 1 if it's a regression problem. But as far as labeling digits, okay, if the number that's written is a 9 and you guess an 8, it is not less wrong than someone guessing a 1, okay? As far as labeling the digits, anything other than guessing a 9 is just wrong, okay? So it's kind of like, try to, it's either labeled correctly or it's labeled incorrectly. Labeling something an 8 when it's actually a 9 is not less wrong than labeling it a 1, okay? Whereas you would use regression if it's like closer is better. So, if it's like, guess how much money we spent, okay? And someone guesses, and you spent $9 and somebody guesses 8, that is a better guess than if somebody guessed $1, okay? So how much money did we spend? Yes, 8 is a better guess than 1. But as far as labels go, 8 is not a better label than 1. So when you have these kind of classification problems, you need to just say it either got the label correct or label incorrect, and so that's why we have 10 nodes in the output layer. So we're going to have to take our labels, which have numbers like the label is 5 or the label is 0, the label is 4, and we're going to have to kind of turn them into basically dummy columns of basically here's a column for, one column for each digit. So this first column, this is when you wish it was 0 index. This first column represents digit 0. The last column would represent digit 9, okay? And so that first image has a label of 5, so it has a 1 here, okay, in this column. The next image has a label of 0, so it gets a 1 here and 0 everywhere else, okay? So that's this is how our labels are, okay? This fifth image has a label of 9, and so it has a 1 here and a 0 everywhere else, okay? So it's having trouble plotting this. Okay, so here, so show the okay, so we're gonna run the same kind of thing. So now I'm basically using the exact same code that I had that we went through earlier. This time I'm going to say my input layer has 784 nodes. Okay, my output layer will have 10 nodes, and my hidden layer I have just arbitrarily chosen 30 nodes. Okay, so in the video that 3 blue 1 brown, he had just 2 hidden layers and 16 nodes each. Here, our structure, we just have 1 hidden layer because we only did otherwise we'd have to do like more of this backpropagation stuff. So we just have 1 hidden layer, 30 nodes, but we'll go through the process here, okay? So my first weight matrix will have a lot of connections, 784 nodes. Each node is connected to every node in the next layer, so 784 times 30. We're going to have kind of a big matrix there. So you can see the dimensions of W1 is 784 by 30, and then W2 will go by 30 by 10. Okay. Every node in the hidden layer gets connected to the output layer there. Okay. Now, one thing I'm going to do that's a little bit different is we are going to do what's called stochastic batch gradient descent. So my training data has a total of 60,000 images. And so my X matrix is technically 60,000 rows, 784 columns. It's this really big matrix. And I could run it through my matrix to do forward feed, or my neural network, so X times W1, activate that, times W2, activate that. I could do that. But that's a lot of numbers for my computer to multiply together. So to kind of shrink how much we're going to do, okay, rather than doing all 60,000 images, because remember, when you do all 60,000 images, you calculate something for each row, and then you sum them all up, right? And it's matrix multiplied, so the summation is implicit, but really you're multiplying stuff and you're summing them all up for 60,000. It's just going to slow my computer down a lot. So what we're going to do is I'm going to just take really small batches, maybe like 10 rows at a time. This is an arbitrary number. I could have done 50 or 100, but I'm just going to do 10 rows at a time. And this is kind of like, just doing like a small sample, and we'll take 10 rows, we'll calculate the gradient based on those 10 rows, which says, hey, uphill is in this direction, and you take a step backwards. And then you go to the next 10 rows, and then you say, hey, what's the gradient based on these 10 rows? What's the gradient based on the next 10 rows? And this will just kind of allow us to speed up our gradient calculation, even though, and eventually I'll go through all 60,000 images. But I'll just go through all 60,000 images once, doing 10 at a time. And that'll kind of just speed up our calculations. And if we wanted to, we could go through it all over again, but it's just going to be faster than trying to do all 60,000 images all at once. Because at the end of the day, you can really only go in one direction, right? So gradient's always going to be pointing in one direction. And so, the gradient is basically the average. Like for this image, it says, if you want to get my image right, you got to point in this direction. And then a different image says, if you want to get my image right, you got to point in this direction. And you're just kind of averaging all of these different directions all together. And so, you could average all 60,000 and you'll get like the true direction that you should go down. But you can just say like, all right, here's 10 images. They all kind of point in different directions. The average is going to be over here, which is probably kind of in the similar direction as doing all 60,000, even if it's not in the absolute same direction, kind of probably in a similar direction. And overall, we'll get it right at the end of the day. So that's what we're going to do. We're going to do just batches of size 10. Okay. And then I'm going to do gradient descent for all of those different batches. Okay. So we're going to scale them down, divide every number by 255, and then we're going to say, make your predictions. We do forward feed, get our new predictions y hat. Our gradients, these are the exact same lines of code from before. Calculate the gradient with respect to W1, gradient with respect to W2, and then update our current values of W1 and W2. So this is 60,000 rows. We'll run it. It takes a few seconds to go through all 60,000 images. Okay, it's done now. And now that we have, now we have values for W1 and W2. So again, here are my values for W2. These values mean nothing to us, okay? But we have 30 rows, 10 columns of values. But now that we have W1 and W2, we can take those matrices and apply it to our test set. Okay, so here's our test data. I'm going to go ahead and do forward feed to get my y hats. Okay, and so the y hats, let me just kind of round them to like 4 decimal places. Oh, shoot. Okay, and so remember the outputs, the true answer is going to be like 0, 0, 0, 0, 0, and then here we have something close to 1, okay, and 0, 0. So this means this first image, it's pretty confident that it's going to be digit 7, right? Because this first column corresponds to digit 0, this last column corresponds to digit 9. So we can kind of check and verify, like, is that digit 7? So we can say, hey, what is the image? So guess number 1. So what I'm going to do is I'm going to ask it to try to guess each of these things, and we're going to just say, hey, which column in each row has the max value? And so here the column with the max value is this column, the 8th column, which corresponds to digit 7. So we're going to just say, hey, take the max column, subtract 1. And then so what's the first guess? The first guess, we guessed a 7, and we can plot it. And indeed, that looks like the number 7. Okay, the second row, we have a 0.8863 here. So this corresponds to digit number 2. 0.05. These are not, these aren't probabilities. They're just numbers close to 1. Okay, and so this says, okay, our guess is a 2. We can plot that, and yep, that looks like a 2. All right, what's the next guess? The next guess is a 1. What does that look like? It looks like that. The next guess is a 4. We can plot that, and that's the 4. So we can kind of do a test, or I guess what we call a confusion matrix, and we can say, what did our neural network predict versus what was the actual value? And what we want to see is a whole big numbers down the diagonal to indicate that when our network guessed a 0, the actual value is a 0. When our network guessed a 1, the actual value is 1. So we want to see kind of values down the diagonal. Okay, so our results table looks like this. Okay, I guess guesses across the column and actual down there. So when the actual was a 0, we guessed 0 941 times. Sometimes we guessed a 2, sometimes we guessed a 6, sometimes we guessed a 7 or an 8. Okay, when the actual value was a 1, we guessed a 1 113 times. You know, and so anything off the diagonal is an incorrect guess. So it looks like 5, we messed up a lot. So when the actual number was a 5, we guessed a 3 fairly often. We guessed a 6 sometimes, okay? That's like understandable. If the actual value was a 9, we guessed a 7 sometimes, okay? And so we can kind of just say like, okay, how many did we get correct? So we got around, out of 10,000, we got 9,251 right. So we're at around 92.5% accuracy, which, you know, I think is okay, considering that this is just a very simple neural network, one hidden layer, 30 nodes. And again, if you go through the script, there's nothing in this script that's like mystery. It's just we're doing some matrix multiplication, we're calculating gradient, updating our gradient there, okay? We can take a look at like which, where did we make a mistake, okay? So these are all of the mistakes that we made, all right? So observation number 9, we made a mistake, okay? And so the actual label on observation 9 was, the actual label is a number 5. And again, we know this because when we did look at the address, it's like Beverly Hills, so we know that the digits should be 90210 or something like that, okay? What does the digit look like, okay? So we go, oh, okay. So the actual label is a 5, and we can kind of see that, but we're also not really mad at our neural network for getting this wrong, right? What did the neural network guess? It guessed a 6, okay? We can say, oh, I can kind of see that, all right? But, you know, it's not like sometimes the neural network did do a bad job. So like I think this one, it got number 16 wrong. The actual value is a 5. It guessed a 3. What does it look like? And yeah, we go, no, you should have got that right. That is definitely a 5, okay? But it guessed a 3 or something. And we, like kind of, but not really, okay? So, and you can kind of go through and see like, other digits, like, I don't know, 8,086, what was that? Right, so the actual value was a 4. It guessed a 6. What does it look like? Okay, yeah, that should have been a 4 or something. But overall, 92.5% accurate, which, as far as a very simple neural network goes, I think is reasonable. And certainly, probably with a bigger neural network, if we add some other terms and add some more flexibility, we can probably get even better accuracy. But anyway, this is an introduction. I think just kind of a neat application of gradient descent as far as finding our optimal solution, or finding not necessarily the optimal, but like a good set of weights to use for like our W matrices and things like that. Okay, so we'll go ahead and wrap things up here for now. Good luck as you study for your midterm exam, which will be on Thursday. So we will see you then. You can, yeah, I guess I might send out a seating chart. We'll see. Okay, but we'll see you guys on Thursday for the midterm. Okay. Oh, I need to give you more view quiz answers, right? Okay. Sorry. Thank you. All right. Answers 3 and 4 are the letter B. So it's B and B. Okay? B and B for answers 3 and 4. Okay. All right. That's it. Have a great rest of your day, and we'll see you Thursday.